In this video, I will show how to perform multiple linear regression in MS Excel. So let's start. We have a hypothetical dataset which has 25 observations with one dependent variable and 3 independent variables. To perform multiple linear regression in Excel, click Data, Data Analysis, go to Regression and input variance. Now input the X range. As we have selected the first row which contains the labels of the variables, check labels. Here constant is 0 actually means the model which has no intercept. So we would not go to that model. You can check confidence labels. Now you can choose the output range. If you need to analyze the residuals, then you can check residuals plots, standardized residuals, and line fit plots. Also you can check normal probability plots. And okay, here's the output. Here we have 25 observations and 3 regressors. The multiple linear regression model is of the form y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. The fitted model here obtained as 26.603 plus 2.895 x1 plus 1.896 x2 plus 0.528 x3. The R-squared value is 0.96. That means about 96% of the total variance in the variable y, that is the response variable, is explained by the regressor variables x1, x2 and x3. For the interpretation of R-squared, in general, the higher the R-squared value, the good the model is. So we have higher value of R squared, so we can think the model as a good model. Now in the ANOVA table, see that for the regression df is 3, for the residuals df is 21 and total df is 24. Now for test of significance of regression, that is the overall or global test of model adequacy. This test determines if there is a linear relationship between the response variable and the regressor variables. So the null hypothesis is set as H0 such that beta 1 equal to beta 2 equal to beta 3 equals to 0 against the alternative hypothesis H1 such that beta j not equals to 0 for at least one j equals to 1, 2, 3. Look at the F-statistic. P value for the F-statistic is very close to 0. We can reject the null hypothesis and conclude that at least one regressor contributes significantly to the model. That means we can say the variable y is related to the variables x1 and or x2 and or x3. Now coming to the test for individual regression coefficients. For this test, we have to set the null hypothesis for the regression coefficients as H0 such that beta 0 equals to 0 versus the alternative hypothesis H1 such that beta 0 not equals to 0. This is for the intercept. Similarly, for beta 1, beta 2 and beta 3, we have to set the null hypothesis against the alternative hypothesis as shown. So look at the t-statistic with its p-value. For the intercept, the p-value is very close to 0, so we can simply reject the null hypothesis and can say that the model has a significant intercept. For the variable x1, the coefficient beta 1, which is a t-statistic 16.53 with a p-value of very close to 0. So we can also here reject the null hypothesis and conclude that the variable x1 contributes significantly to the model. Similarly, for the variable x2, conclude the same prediction. x2 contributes significantly to the model. But for the variable x3, the regression coefficient beta 3 has a t-statistic 1.27 with a p-value of 0.218, which is greater than 0.05. So for the null hypothesis beta 3 equals to 0, we are actually failed to reject the null hypothesis. That is, the coefficient beta 3 is not significantly different from 0. That is, the variable x3 doesn't contribute significantly to the model. So for a better model, we can exclude the variable x3. When we exclude the variable x3, the model becomes here. Select x1 and x2 only and run the model again. Compare these two models. The first one is with x3 and the second one is without x3. So the first model have r squared 0.96 and r squared value 0.95 in the second model. So not so much different, and these two model becomes the first model is y hat equal to 22.603 plus 2.895 x1 plus 1.896 x2 plus 0.528 x3. When we exclude the variable x3, the model is y hat equal to 23.803 plus 3.013 x1 plus 1.83 x2. So in the second model, all the three regression coefficients are significantly different from 0. That is, the variable x1 and x2 contribute significantly to the model, and the intercept is also significant. But in the first model, x3 doesn't contribute significantly to the model. So when we compare these two models, the second one is more preferable than the first one, as the variable x3 has less contribution, actually not significant. Now look at the adjusted r squared. In the two variable model, it is 0.9482, and for the three variable model it is 0.9496. Almost the same. The difference is not actually mentionable. Therefore, we can conclude, comparing these two models, we can conclude that Adding variable x3 to the model doesn't result in a meaningful decrease of total variability and doesn't improve the model's explanatory power significantly. So it is better to consider the regression model with two variables only, and the simpler two variable model can be preferred for its parsimony unless there are other practical implications and specific relevance of including variable x3.